Okay, it's 8:30. Let's go and get started. Good morning, everybody. How's everyone doing today? I'm good. I'm good. Riveting audience here today. It's busy. It's a busy week. I know. It's also 420. So if you are going to partake in that, enjoy yourself today. I think looking back, I can't believe I scheduled a midterm for today because that was kind of a poor choice. Although I guess after the midterm, our class is first thing in the morning, so I guess afterwards you could choice. So, yeah. Okay. So the theme for today, we're going to continue on with our lecture on probability and statistics. Okay. So hopefully, I'm hoping that a lot of today is kind of more or less review, or maybe you maybe heard of some of the things that we're going to talk about today, but you haven't really seen the hard definition. And so, because we're going over things like mean, median, and mode. Different data representation, different representations of data like histograms, things like that. Okay. All right, and so hopefully everyone got my email earlier this week. So the midterm again is a week from today, so it's going to be on April 27th. That is next Thursday. The probability and statistics stuff will not be on the midterm. So the midterm will just be on the multivariable calculus stuff, the line integral, surface integrals, and all of the Fourier stuff, so Fourier series, Fourier transform. Okay. But the probability and statistics stuff that will be on the final exam, so we need for that. Okay. So remember, homework 6 is due this Sunday, and so make sure you get that in before the deadline. It's fairly short homework, so I'm hoping it doesn't take you too long. It's just a few basically integral transforms, so. But of course, if you're having trouble with that, if you have any questions, definitely come by office hours. Remember, I have office hours right after the lecture on Thursday, so from 10 to 11. So you can either join in person or you can join on Zoom. Okay, all right. So that's all. That's everything I have to say for announcements. Are there any questions I can answer before we get started for today? Okay, all right. Let's go and get started. And we left off last time talking about representation of dates. And so whenever you have any kind of situation where you're collecting data and that data changes every time, there's different ways that you can represent. Okay? And today we're going to start with graphical representation. So again, this is kind of a big shift from kind of the rest of the topics in this class, where the rest of the topics I would consider to be, like fairly advanced, like linear algebra, different equations, calculus. This kind of goes back to more kind of experimental. This is much more on the experimental side. So you're going to use a lot of the methods and a lot of the mindsets that we're going to go over here in kind of your lab classes, if you haven't already. Okay. Okay. And so when collecting data, and you can collect data for a lot of different things. And so, it's kind of hard to summarize it in one sentence, but, I'll do my best. And so when collecting data to observe a certain phenomenon, and so like in your lab classes, you'll be collecting data to observe some kind of physical phenomenon, to prove some kind of physical law, things like that. Okay? Or maybe you're just interested in collecting data just for your own life. And so remember last time we went over an example of, keeping data or keeping track of how long it takes to you to school, how long it takes to do so whatever reason you're collecting data, it's always useful to present it in a way where you can easily see the trends. Okay. And that's ultimately what we're looking for, when we have a large collection of data. So what are the trends? What are the data entries that appear most often? What are the data entries that appear less often? Is there a relationship between certain areas of the data? And so we want to see these trends. And a lot of times you have to view the data in some kind of graphical format to see those trends. Okay. So I'm going to go over a couple common ones that you'll see. Okay. First is a histogram. And so the idea with the histogram is to represent the data by sorting them into particular bins based on their data. Right, so it's almost like sorting your laundry. So you take your data, depending on its value, you throw it into a particular bin. Okay, and then the amount of data in each bin represents the frequency of how much that value shows up in your data set. Okay. And so, of course, these are best visualized by an example. And so let's say that we want to make a histogram of the heights of NBA players. Okay. And so we're going to take every single player in the NBA, and then based on their height in inches, we can make a histogram of that. Okay. Okay, so it would look something like this. So usually a histogram is displayed like this. And so on the horizontal axis, okay, on the horizontal axis would have the height inches. Okay. And then what you'll see is that on the horizontal axis we'll have kind of different values for the height. Okay. And so for instance, let's say that we start over here, 65 inches, 70 inches, 5 inches, 80 inches, and 85 inches. Okay. Okay. And so if you know anything about basketball, it helps if you want to be a professional basketball player, it helps to be tall, right? There are some very short NBA players, and they are an inspiration to people like me. Not that I would ever make it out to be in the NBA, but just to put it out there. Okay. So generally what you're going to see is that a lot of this histogram is going to be skewed towards the right, towards the higher values of height. Okay. And so you might have something like this. And so you may have a couple outliers. Okay. So maybe you have a couple NBA players that are really short, but generally speaking, as you go to the right, you're going to see a lot more and of course, there are outliers on the other side as well. Okay. And so if you look at my height, I'm about 5'4", so I'm right about on the lower spectrum there. And so that's about 64 inches. But generally speaking, NBA players tend to be tall. Right? Okay. And so what does this histogram show us? And so this shows us that, out of all the NBA players, you're much more likely to find players in this kind of height range right here. If you look at kind of the two largest bins, that shows us that most NBA players are kind of in this range. Okay. We have your outliers. Maybe you guys are too young for this, but when I was growing up, there was a player called Nate Robinson. So he was just about my height, but he was spectacular in that he was very good at dunking the basketball, and so he could jump really, really high. And so that little bar there is for Nate Robinson over there. And on the other side, you have players that are just ginormous, like 7'2", 7'3", 7'4". And so those are kind of outliers on the other side. All right, any questions on histograms here? Okay. All right, so histograms are very popular, and I think generally they're generally relatively easy to interpret. They're almost like a bar graph. You can almost interpret it like that. Okay. A popular way of presenting data is to use what's known as a box and whisker. Which I always thought was a very funny name, but I guess it kind of makes sense when you know what it is. Okay. And so the whole idea with the box and whisker plot is to kind of illustrate this idea of where the way the box and whisker plot is that it kind of shows you where most of the data is clustered. Okay. And so that's what the box is going to show. So the box shows where most of the data of your data set is clustered. Whereas the whiskers kind of show you the values of all the outlines. Or maybe I should have defined outliers. And so when I talk about outliers in the data, what I mean are certain entries in the data that kind of drift far away from the trends, so drift far away from the means, and where most of the other data is, and they're so far away that they're considered, outliers, kind of outlandish from the data. Okay. And so a box and whisker plot would look something like this. And so let's use the same example. And so let's use the same example of heights of NBA players. So box and whisker plot, it could be shown either horizontally or vertically. I've seen kind of both, but I'll show you kind of a vertical version of the box and whisker plot here. Okay. And so the box of the box and whisker would look something like this. Okay. And so this box right here tells you that most of your data or most NBA players have heights within this range. But then, outside of this range, we do have some data outliers. So we have some data that's kind of outside of here. And those are represented by the whiskers. And so, you'll always see the plots that kind of look like this. It almost looks like I guess like a bead on a string. That's kind of how I view it. So those whiskers there are going to show the extent of the outline, right? So remember we talked about, there are a few NBA players that are very short, okay? There's usually like one or two short dudes every year, and so there's always at least one. Okay? And so this bottom whisker right here, these are all the short dudes in the NBA. And of course, the top is all the super tall dudes. I bring the NBA up just because, the NBA playoffs have just started recently. I was hoping to be in a better mood today because, the Lakers played yesterday, but they kind of played pretty bad yesterday, so they lost. But they took game one, so that's okay. One other thing that you'll see in the box and whisker plot is that, while this is kind of useful, it's kind of useful to see where most of your data is clustered. A lot of times you want to see kind of what the median value, so what's the absolute middlemost value. Okay? And that's often represented by a 1. You're not always going to see this, but in a lot of box and whisker plots, you do see this kind of red line in the middle of the box. That shows you your median value. And oftentimes it's not in the middle of the box. And so you would think that the median value would be kind of right in the middle of that box, but usually it's skewed to kind of one side or the other. Right? And we'll talk about kind of why that is later on. And so we'll talk about kind of the difference between the mean and the median and why they're often different in a lot of data sets. Okay, any questions on this so far, on box and whisker plots? Okay. All right, I want to kind of stay on this for just a second because I think intuitively, I think this is kind of a good definition here, but it's still a little bit vague. So, in particular, I want to kind of focus on this fact right here. Okay. And so I say that most of your data is clustered within that box. But what does most mean, right? And so when I say most, what I mean by that is that that box that represents data between the 25th and 80th and 75th percentiles of the data. And so if you sort your data from kind of the least to the greatest, then basically the middle 50% between the 25th and the 75th percentile is going to be represented by that box. I wanted to make sure I mentioned that just because if You know, if someone later down the line asks you to draw a box and whisker plot, you kind of know exactly what the definition for that box is. Okay. Okay. All right. So of course, you know, there's lots of other different ways to represent data graphically. I would say, you know, these two are kind of the more useful ones that are there. Besides, you know, your basic bar graph, your basic line graph. You've definitely used those, or cluster plots. You probably used those in your lab classes, and so, you know, I'm not going to cover those again. But you know, when we're talking about kind of random data or data that can have some variance, you know, I wanted to make sure I cover these, you know, just because they're useful for that. Okay. Yes, question.
And for median, is it the median within the box or like the whole data set?
The median of the whole data set. Yeah, so it's rare. Unless if you have very skewed data, you actually might have a median that's actually outside the box. It is very. You have to have a very strange data set, but most times the median is going to be within that box. Okay, so that's all I wanted to cover for graphical representations of data. Let's talk about more quantitative. And so let's start with the review of mean, median, and mode. Okay. So I'm going to go through this fairly quickly just because it's, you know, hopefully it's decent amount of review. So let's start with mean. So the mean is simply the average value of the data set. And so the way you compute the mean is that you add up all the values of the data set and you divide by the number of entries. Okay. And so usually the mean, you know, if you have x, the value variable x that's going to represent the your data, you usually represent the mean with a bar over your variable, right? So you have x bar. You compute this, get 1 over n, where n is the number of entries in your data set. Then you sum up, I is equal to 1 to n, x. Okay. So that's a fancy way of just saying, just add everything up and divide by the number of entries. Or I think what's more common nowadays is to use the equal average function, either Google Sheets or Microsoft. So at least that's what that's generally what I use nowadays too. Okay. So that's the mean, very straightforward. The median is defined as the middlemost value of the data. Okay, so to find the median, you would take your data set, you would order it in ascending order or descending order, works well as well. And then just pick out just whatever the middle, the value that's just halfway down the list. Okay. So mean and median. So it's the same definition as it's always been. So let's talk about the differences between these two. And so I'm sure you probably previous classes have said this before too, but oftentimes people get the mean and median confused, or not confused, but people think that they're basically the same. And for a lot of data sets, they are. And so just whatever the average value of the data set is and the middlemost entry of the data set is, a lot of times they can be the same. But there are a lot of times where you're going to see big differences in between these two values. So for example, so this is old data. So I haven't updated my notes, for recent times. But if you look at the average household incomes of families in California back in 2019. You'll see kind of a good example of the mean and median being different. If you look at the median, this data, the median for this data back then was about $63,787. All right, so the median household income back then was about almost $64,000 per year. Okay. The mean, on the other hand, was much higher, and so the mean 91,140. Okay. That's a big difference. That's like a difference of about 50%, and so the mean is about 50% higher than the median, which is pretty big. Okay. So how did this happen? How do we have such a big difference between the mean and the median? And so these are different just based on the way that they're computed, right? So the mean basically adds up everything and then divides by the number of entries, right? The median really only depends on the order and the number of entries that you have. Okay. The mean, in particular, the mean is subject to, or it's more sensitive to, strong outliers in the data. Okay. And so what do I mean by that? So strong outliers. And so, if you think about it, California, it's a nice place to live, right? And so, the weather today is beautiful. Generally, people like the weather. And so it kind of attracts, a lot of people, a lot of wealthy people in particular, right? And so you have, in California, you have kind of a larger density of people that make a very, very large amount of money. And so a lot of athletes live here, a lot of movie stars live here, a lot of, company CEOs live here. You have a lot of, very wealthy people. And so their incomes are just so significantly higher than everyone else. And what they do is they skew the mean. And so that's why the mean tends to be higher, just because of these very strong outliers. Okay. And so, whenever you're looking at kind of economic reports, or you're looking at kind of how the average family in California is doing, you'll almost always see people report the median. The lawmakers, just data people, just in general, they'll always talk about the median household income, because the median is in this particular case, the median is a much better representation of kind of how the average, just average person in California is doing. And so this case here kind of gives you a cautionary tale. And so, I think when people make articles about this, they say, oh, the median is better, things like that. The median is better in cases like this, when you have very strong outliers, right? Sometimes you'll have data sets where the mean is more representative than the median. Okay. And so it really kind of depends. But when you have data sets with very strong outliers, generally you want to look at the median as kind of a more average case. Okay. Any questions on this? Okay. All right, so that's the mean and median. So let's go over mode again really quickly. So the mode of a data set is simply just the entry that appears most often. And so, the way to find the mode is to, very similar to the median, you're going to order everything from least to greatest, greatest to least, and you're going to see, which entry just appears the most often. Okay. So, fairly straightforward. Okay. And so for data sets where every entry is unique, you don't get to just randomly assign a mode. And so in those cases, you say the data set has no mode. Okay, so that's the mode. So mode pretty much the same as Okay, so let's go ahead and move on to two new metrics that you've probably heard of and probably have a good kind of intuition for what they mean. But we'll go over kind of their exact definition. So that would be the variance and the standard deviation of the case. Okay. So the mean, the median, and the mode, they all kind of express somewhat of the same information. And so the mean, median, mode, they're often grouped together because they give you kind of an idea of what a typical member of a data set looks like. So they all kind of express that idea differently, but it's kind of a look into, if you were to pick something random out from a data set, you would probably get something that looks like the mean, median, and the mode, most likely. Okay. The variance and standard deviation kind of represent something a little bit different. And so what these represent is they represent how varied or how different each data set entry is from each other. And sometimes, that's a very important metric, or so that's something that's very kind of important to know in a data set. Okay. All right, so let's do just a very, very quick example. So let's say I have two data sets. So I'll call it data set A and data set B. Okay. These two data sets are going to have the exact same mean and median. Neither of them have a mode, but you'll see that these two data sets, even though they have the same mean and median, they're going to be very, very different data sets. Okay? So for data set A, we'll say it consists of 5 numbers. And so data set A will be -2, -1, 0, 1, and 2. Okay. And so from that data set, you can see that it's already ordered in ascending order. And so you can see the median of this data set is 0, and the mean is also 0. Okay, so let's look at data set B. And so data set B will be -200, 100, 0, 100, and 200. Okay. And so you can see from these two data sets that they have the same mean. And so if you look at data set B, the mean of this is 0, and the median is also 0. Okay. But data set B is a lot different than data set A, right? And so what's their difference? Or so how can we characterize their differences? In data set B, the amount of space or the amount of difference between successive entries is much larger, right? In data set A, the entries are only separated by just 1, right? So it's really just counting up from -2 to 2, okay? But in data set B, the space in between each entry is 200. Okay? And so, we should have a metric that kind of shows that these two data sets, or that kind of, it kind of like, expresses the difference in these two data sets. Okay? And that metric is the variance. Okay, so let's define the variance. And so the variance expresses, how much each data entry differs from each other. And its formula is given by the following. So the formula it's a little bit complicated, but there's also Excel functions for this as well. And so you can use Google Sheets to compute this as well. Okay, so for the variance, it usually has a symbol sigma squared, and I'll try to show you why it's sigma squared in a second. The way to compute this is do 1 over big N minus 1. Where big N is still the number of entries in the data set. And then you're going to have a summation. The summations go from I is equal to 1 to N of xi minus x bar squared. Xi here, this is the part we're summing over. So this is each individual data entry. Okay. And X bar, remember, this is the mean of the data set. Okay. And so what you're going to sum up is you're basically going to take the difference. You're going to take the difference between each individual entry minus the mean, square it, and then you're going to add that up for every single entry in the or if you're using Microsoft Excel or Google Sheets, you just do equal variance and just highlight everything in the column with it. But it's good to know where the formula comes from. Okay. So that's the variance. And so now let's define the standard deviation. And so the standard deviation is simply just the square root of the variance. And so standard deviation usually has the symbol sigma, and sigma is just square root of sigma squared. All right, so the reason standard deviation exists is that if you look at the units, for the variance, you'll see that it has the units of the data squared, right? And so because of this square right here, because of the square, the variance actually usually has different units than the actual data itself. Okay. And so oftentimes, when we talk about differences between data entries, we usually want to talk about it in terms of the same units of the entries themselves. And so that's where the standard deviation comes in. So it just put the differences in the same units as the original data. Okay. And so you may be wondering, or maybe not, I always wonder this, but maybe I'm just weird. But you may be wondering, why do we bother with the square anyway for the variance, right? And so it seems like standard deviation is kind of the more intuitive way to think about things. But the reason we square things for the variance is to make sure that the variance is always positive, right? Because when you subtract the mean away from a data set, you're always going to have entries that are positive and negative in terms of either above or below the mean. Okay. But what you're characterizing here is you want to look at kind of the absolute, almost like the absolute value of the differences. Okay. And so one way to get kind of make sure you always get a positive number is to square, right? You have two negative numbers, you square it, then it becomes a positive number. Okay. You'll see this a lot in math, and so you'll see this a lot when you want to get a positive number. Instead of taking just an absolute value, they would just square stuff. And I don't know if it's because absolute value wasn't invented until way later after squares, but a lot of mathematical theory is based off squares instead of absolute values. I will say absolute values are a little bit, how should I say, not elegant in math, and so squares are a little bit more elegant, but it creates some issues. But anyway, I'm just ranting. So okay, any questions on variance or standard deviation? Okay. So those are the main metrics. And so now let's go ahead and move on to random variables and probability distributions. Right. So when we first started talking about probability and statistics on Tuesday, I brought up the fact that there are certain phenomena or certain events that occur that have a different value every time you observe them, right? And so the example that I used here was your commute time to school, right? It's hard to put a precise value, or I would say it's impossible to put a precise value on the amount of time it takes you to drive to school, because of factors that are outside your control, because of uncertain factors. Okay. We have formal kind of mathematical theory for these types of phenomenon. We call them random variables. So random variables have the definition where these are variables that take on a different value every time we observe them. And so, for example, we can use a random variable to represent our commute time. Because every time that you measure it, every time that you observe it, every time that you drive to school, okay, it's going to be different because traffic's going to be different. The weather's going to be different every day. The stoplights are going to be different every day, right? And so every time you observe it, it's going to give you a different value. Okay. And so Tuesday, remember I also talked about when you deal with random variables rather than deterministic variables, we kind of need to kind of expand our mathematical tool set in order to deal with these. And so the way that we kind of characterize random variables is through, part of it is through kind of what we just went over. So things like mean and variance and standard deviation, median and things like that. Okay. But we can also use probability distribution functions to describe their behavior as well. And so it's a lot more complicated to describe a random variable. There's kind of no way around it. Right? And so instead of having a single value, there's lots of different ways we can describe it. All right. And so remember I mentioned this on Tuesday too, but when I say random, I don't really mean random in a true sense, right? And so if your commute time were truly random, then it would be every day it would be like if your commute time was truly random, then sometimes it would take you maybe 10 seconds to get to campus, but maybe sometimes it'll take you 8 hours to get, right? So it's not pure chaos in that sense, right? So that's what I would call pure chaos. And so even though random variables, they take on a different value every time that you observe them, they still follow some rules. And so there's still some bounds that kind of guide their behavior. Okay. And so one way that you can describe those rules is through, things like its mean and its variance, which we've covered. Okay. But another way, kind of a more precise way to kind of govern these rules is through looking at their probability distributions. Okay. So let's go over that. All right, so let's start with the distribution function. Okay. So, people, it's interesting. So when I first learned about random variables, I thought they were just a huge pain in the ass because they can't have a single value. And so just to describe one random variable, you need a whole ass function to describe it, right? And of course, as fate would have it, one of the things I hated the most about math as an undergraduate, I ended up working with a lot in grad school. So a lot of the research that I did in grad school was under basically like a field called uncertainty quantification. And so I was basically working with random variables for 6 straight years. And of course, I learned to love it after a long time, but it took me a long time to really like it. Okay, so let's start with the distribution function. So the distribution function, this is associated with the random variable. So for a random variable, Okay, so let's call it X. And usually the convention, or at least the convention that I see most often, is that for random variables, we typically use uppercase letters for random variables. Okay, and so for random variable X, the distribution function gives us the probability that when we observe X, okay, so when we take its value, the distribution function gives us the probability that X is less than the function variable T. And so usually distribution function is given by the symbol we use for it is capital F. Okay. And then in the subscript of the distribution function, we give the symbol for the random variable. Okay. And so for the distribution function for a random variable X, we do F sub X. Okay. And that's going to be a function of some variable. So T here doesn't really represent time, it's just a dummy variable. Okay. And so what it represents is the probability that X is less than or equal to T. P here stands for probability. Now we're kind of getting into the realms of probability, where things kind of have a chance to happen based on the probability. Okay, so let's give an example so you can kind of illustrate, how this is. Let's define a distribution function to describe our commute time. Okay. So let's define our commute time as a capital T. And so we're going to define the distribution function. Okay. Okay. So distribution function, we'll call it big F. And then we're going to do sub will T. Okay. And what I'm going to do is I'm not going to give you a functional form for this, but we're going to define it as particular values. Okay. And so let's say that we're going to define the value for ft of 10 minutes. Okay. And so what this is going to represent is the probability that our commute time, right? So basically the percent chance that our commute time is going to be less than 10 minutes. It's going to take us less than 10 minutes to get to campus. Okay. So let's say that this is, well, I mean, from where I live right now, this is literally a 0% chance, but let's assume that we lived a little closer to campus. We'll say that this is a 5% chance. Okay. So that's if you hit all green lights, you know, there's literally no other cars on the road, then you can get to campus in less than 10 minutes. Okay, so now let's do 12 minutes. Okay, so our distribution function at 12 minutes, which is the probability that our commute time is less than or equal. Okay. So this gives a little bit more leeway, and so you know this gives you more time for the traffic's going to occur for traffic lights. Okay, let's say this is about 35%. Okay, so now let's do 15 minutes. And so the probability that your commute time is going to be less than 15 minutes, let's say that this is around 80%. And so you can see is that as the value for t, or I guess for little t here, is increasing, go from 10 to 12 to 15, our probability is increasing, right? Because then that tells us that, our commute time is going to be somewhere usually between 10 and 15 minutes, most of the time, 80% of it. And then as we get higher and higher, this percentage is going to get higher, okay? And so the probability that your commute time is less than 20 minutes is up to 95%. And then once you get to an extreme value, so let's put this at an hour. This is basically going to be 100%. It's not quite 100% because there's always a possibility, and heaven forbid, you get into an accident or something, or your car breaks down, or something happens. Okay, so it's never quite 100%, fully 100%, but it's effectively 100%. Okay. So that's how distribution functions work. Any questions on that? Okay. Another name for a distribution function and this is the name that I kind of see more often in the literature, is the cumulative distribution function. So we just added a C word to the beginning. Usually we give it the acronym CDF. And so if you see CDF, CDF stands for cumulative distribution. Okay. And so one feature of the CDF, or one feature of the distribution function that you probably noticed already, is that because of the way it's defined, a CDF is always monotonically increasing. And so if you've never heard that term before, monotonically increasing, what that basically means is that the function is always increasing in value and it never takes a point where it actually decreases. Okay. All right, and so if you actually plot this, okay, a lot of CDFs are going to look like this. So it'll be 0 for a while. It'll be a point that moves up. And it just kind of stays up just like that. Okay. Typical. Where the maximum, it depends on how you define probability. So some people like to define probability as a percentage. And so the maximum value here, of course, is going to be 100%. But some people also like to represent probability as definite. So you might see the maximum be 1. So 100% or 1, you know, it's kind of up to you. Depends on how you define probability. Okay. One neat thing that you can do with the CDF or the distribution function is you can compute the probability that your random variable lies within a certain range. Because right now the distribution function, the way it's defined is that it just gives us a single value for, you know, if our random variable is less than a certain thing. Right? But what if we want to compute the probability that, you know, what if we want to compute the probability that our random variable lies between this range? Okay. Or this would be, you know, some lower bound A, this would be some upper bound B. Okay. So we can do that. And so the probability that A is less than or equal to X, is less than or equal to B, is equal to, we're going to take the value of the CDF at the upper bound, so X at B, minus the value of the CDF at the lower bound, Fx at X. All right, any questions on this? Okay, so the last thing we'll cover today, and we'll probably pick this up again on Tuesday, is this idea of a probability density. Otherwise shortened to PDF. Having no relationship to the file format. It just happens to have the same initial probability density. Okay. Okay. So CDFs are, you know, I think are intuitively are kind of easy to interpret, right? And so it's all based on this idea of probability. Okay. But in terms of actually describing how a random variable behaves, visually it's not the nicest thing. Well, I guess it depends on your preference, but personally, you know, I think, you know, seeing a function here that's kind of always increasing, it doesn't really tell you a lot about how the random variable behaves, right? But it's hard to pick out from this plot here, you know, what a typical value is, right? If you were to sample the random variable, you know, it doesn't really give you a sense of, you know, what's a typical average, or what's a typical member. And a lot of times, you know, when we're looking at a random variable or we're quantifying it, that's kind of what we want to know. It's one of the things that we want to know is, you know, what is the most likely or the expected value of this random variable. Okay? And that's a little bit hard to pick off from a CDF. And so, from this idea, the idea of a probability distribution function was kind of born. But to kind of introduce this idea, let's kind of go back to kind of the beginning of part of the class today where we talked about histograms. Okay. And so if you recall, histograms are a graphical representation of the frequency of certain data entries in a set. And so the more a data entry shows up, the more likely it is that if you were to pick an entry in a data set at random, right? So close your eyes, just pick one out of a bag, right? The histogram shows you, which entries or which values are most likely to pick out from the bag. Okay. And so the PDF or the probability distribution function is kind of the formal mathematical kind of form of this thing. Okay. Actually, let me write that down. Okay. Right, so for the histogram, for the entries where the bars are much higher, you're going to think that those are going to be much more likely that you select something from that bin. And so if we draw a histogram, let's say that we have kind of a histogram that looks maybe something like this. Right, so that's kind of what a typical, maybe a typical normally distributed histogram would look like. What we can do is, we can look at this bar graph and say, let's superimpose a smooth function on top of this. And so if we were to impose a function, maybe it looks something like this. And so that function that we can impose on top of a histogram is exactly the probability distribution. Okay. So that's kind of the visual kind of interpretation of a PDF. The quantitative definition is that you can obtain a PDF by simply taking the derivative of the CDF. Okay, so it's PDF. Usually we give it a lowercase f x of t is equal to the f x d t. Okay. Right, so the probability density function is closely related to the distribution function, to cumulative distribution function, by a simple derivative operation. So if you take the derivative of the CDF, then you get. Right, it's way too many acronyms, so we'll go over this again on Tuesday. All right, any final questions on this before we wrap it up for today? Okay, all right, so that's all we got time for today, and so we'll wrap it up here. So Tuesday we'll pick it up here and talk more about probability density functions. We'll talk about Gaussian distributions, and we'll talk about the bell curve and all these terms you probably heard before. Okay. And then Thursday we have our midterm exam. Okay, so thanks everyone for coming today. I hope everyone has a good weekend. Remember, homework 6 is due Sunday, so if you have questions on that, let me know. But if not, hope you guys enjoy the weekend, and I will see you next week. Yeah. Yes, and so both of those would be considered a vote.
What if, like, where's the cutoff between, like, what if you have then like 3 repeated numbers, so like 10 repeated numbers, like, so then you only have like 11 points and 10 are repeated, or there be 10 modes or just no mode at that?
Yeah, so it would be, I mean, technically speaking, you would have all of them would be modes,
Oh,
but it would be the one, if you have one that appears most often, so if you have like one entry that, or 2 entries that appear 3 times, and you that appear 3 times, then it would be the 2 that. Yep. Yeah.
You said ask the witness.
For 410. So usually, I usually do. So I usually try to be as generous as I can with the wait list. And so for that class, I've accepted, but that's if I'm teaching. So I don't know. But we are usually I do, because among the people that work here right now, I'm doing one. But we are hiring people, so they may teach them. If it's me, then I'll work that. Jason, any final questions? So do we have this? Everything else is not.